What if I told you that the plastic in your biodegradable cup, the preservative in your food, and even some medicines you use daily, all start from corn sugar? Today, we're diving deep into the industrial manufacturing of lactic acid from corn sugar, a process that combines biology, chemistry, and large-scale engineering. Stick till the end, because we'll also talk about PLA bioplastics, market demand, and why lactic acid is one of the most important biochemicals of the future. Let's begin. Lactic acid is an organic acid with the chemical formula C3H6O3. It's a colorless or slightly yellow liquid with a mild acidic taste. It is completely biodegradable and naturally produced by various bacteria, making it a sustainable building block for global industry. Its applications are incredibly diverse. In the food industry, it's known as E270, used for preservation and flavor. In pharmaceuticals, it's a key ingredient in many life-saving medicines. Beyond food, you'll find it in cosmetics for skincare, in textile processing, and most importantly, as the precursor to PLA bioplastics. And the cleanest, most economical way to produce this essential chemical at scale today? The microbial fermentation of corn sugar. Corn sugar, also known as glucose or dextrose, is derived from cornstarch. Industry prefers it for several critical reasons. First, it's a renewable raw material. Second, it offers high fermentation efficiency and consistent quality, which are vital for large-scale operations. And finally, it's low cost in bulk production. This combination makes it the ideal fuel for the microbial fermentation at the heart of lactic acid manufacturing. The process starts with a precise mix: corn sugar solution, water, and nutrients like nitrogen and minerals to sustain the microorganisms. We also need neutralizing agents, typically lime or calcium carbonate, to manage the acidity during the reaction. More on that shortly. Then there are the workers, bacteria like Lactobacillus delbrecki and Lactobacillus plantarum. These tiny engines are the ones that actually perform the conversion. Now, we enter the most critical stage of the entire process: the fermentation. This is where the magic, or rather the chemistry, happens inside massive industrial fermenters. First, the glucose solution is sterilized to prevent any unwanted contamination. Even a tiny trace of foreign bacteria can ruin an entire multi-ton batch. Next is inoculation, where the selected Lactobacillus bacteria are added. From here, we transition to strictly controlled conditions. We maintain a temperature between 30 and 42 degrees Celsius and a pH of 5.0 to 6.5. This process is anaerobic, meaning it happens without oxygen. Over 24 to 48 hours, the bacteria produce lactic acid. But here's the challenge. As the acid concentration rises, it lowers the pH, which eventually stops the bacteria from working. To keep the process moving, we add calcium carbonate or lime. This neutralizes the acid as it forms, allowing the bacteria to continue their work efficiently. During this neutralization, lactic acid reacts with the calcium carbonate to form calcium lactate. This is a crucial pivot point in the production chain. This step is vital because it prevents bacterial inhibition, maximizes the overall yield, and makes the subsequent downstream processing significantly easier. But remember, we don't want calcium lactate. We want pure lactic acid. To get there, we need to enter the separation and purification phase. The first step is solid-liquid separation. We use filtration or centrifugation to remove the bacterial cells and any remaining solid particles from the liquid broth. Next comes acidification. The calcium lactate is treated with sulfuric acid. This releases the lactic acid and creates calcium sulfate, also known as gypsum. The gypsum is filtered out as a solid byproduct, which is actually quite valuable for the construction industry. This is a classic example of zero-waste engineering. Now we focus on purification. We use activated carbon treatment to remove any unwanted color or odors, ensuring the product meets high industrial standards. Then, we pass the acid through ion exchange resins. This process removes any remaining ions and inorganic impurities, leaving us with a highly pure solution. Finally, vacuum evaporation is used to concentrate the acid. By lowering the pressure, we can boil off excess water at lower temperatures, preserving the acid's quality. The final lactic acid concentration varies by its intended use. Industrial grade is typically around 80%, while high-purity food and pharma grades reach up to 90%. The finished product is stored in specialized stainless steel tanks and packed into drums or containers for distribution across the globe. But let's not forget the byproducts. The gypsum we mentioned is essential for cement and construction, while the residual biomass is often used as high-quality animal feed. Modern lactic acid plants are designed with zero liquid discharge in mind, focusing on energy recovery and total resource utilization. This is green chemistry in action. The most exciting application today is polylactic acid, or PLA. By polymerizing our pure lactic acid, we create a fully biodegradable plastic. You'll see it everywhere, from the disposable cups at your local coffee shop to advanced food packaging that breaks down safely in the environment. It's also revolutionized 3D printing and even the medical field, where it's used for dissolvable stitches and advanced orthopedic implants. This is why global demand for lactic acid is exploding. With an annual growth rate of over 8%, it's becoming one of the most strategic biochemicals on the planet. As nations move to ban single-use plastics, corn-based lactic acid plants are becoming critical infrastructure for a sustainable, circular economy. Investing in these technologies isn't just about making a product. It's about decoupling our material needs from fossil fuels and building a cleaner future for industry. At SimpleGen, we believe that understanding these invisible backbones of our world is the first step toward innovating for the next generation of engineers and students. If you found this deep dive valuable, hit that like button and subscribe. Your support helps us simplify more complex industrial processes for everyone. What manufacturing process should we tackle next? Comment below with your suggestions. We read every single one of them. We want to know what you want to understand next. Because here, we don't just learn, we understand how the world is manufactured. This is SimpleGen, signing off.